So the question now is, can we go on forever? Or when do we stop? Do we have to stop? And that's a very subtle question. There are inequalities available that allow you to choose the degree of the polynomial when you want to approximate your function to a certain accuracy. However, in the theory, at least, we don't have to stop. We can take n as big as we like and then go from a polynomial, Tn of x, to a series, T of x. So we can define the Taylor series of the function f at the point A as the limit of the Taylor polynomials as n goes to infinity. Formally, we can write it down, as you see on the slide, either using the simple terms in our series, or we can also use the sigma notation that you see at the bottom. So T of x is the sum from 0 to infinity of the nth derivative of f at the point A divided by n factorial times x minus a to the n. Such a type of series is known as a power series. If you like, it's a series of polynomials, or sequence of polynomials rather, where the degree increases to infinity. And this is a series I want to use in the following and describe a few applications of. Now there's a special case when a is 0. You see, everything that happens then is that instead of x minus a and x minus a squared, you have terms x and x squared, and so on. In this special case, the series looks a bit easier to compute, and it is called the Maclaurin series of the function f. But it's nothing new to learn. The Maclaurin series is just a special type of Taylor series. So let us finally compute the Taylor series of the function log of x at the point x is equal to 1. Remember from the formula of the Taylor series, all we have to do, well, we have to compute the derivatives of f at each order. So this could be quite tricky, but for our function, it is not too hard. We already had the third derivative, which was 2 times x to the minus 3. And so at x is equal to 1, this derivative is just 2, or again 2 factorial. Now we differentiate again and again until we can spot the patterns in the derivatives of f. So let's compute the fourth derivative. Well, let's differentiate 2 times x to the minus 3. This gives minus 6 times x to the minus 4. And if we sub in x is equal to 1, we get minus 6 or minus 3 factorial. Differentiating this again, minus 6 times x to the minus 4, we find the derivative is 24 times x to the minus 5. So the fifth derivative at 1 is 24 or 4 factorial. So now we can already see what happens. The derivatives of f, they change sign from the derivative of order n to the derivative of order n plus 1. So the sign of this derivative changes at each step. And moreover, we always multiply the derivative at the order n by n to get to the derivative of order n plus 1. So in general, we can write that the derivative of the logarithm of x of order n is minus n to the n minus 1 times n minus 1 factorial times x to the minus n. And if we sub in n is equal to 1, then we find that the nth derivative of f at 1 is minus 1 to the n minus 1 times n minus 1 factorial, because x is 1. So there's a general formula for the derivatives of f, and now we can use this to plug it into our Taylor series. We can now write down the Taylor series of f of x at x is equal to 1 simply by using this general formula. Remember, our derivatives are minus 1 to the n minus 1 times n minus 1 factorial, and we divide these by n factorial in the nth term of the Taylor series. Now n minus 1 factorial divided by n factorial just leaves n in the denominator, and so as a Taylor series we get the general formula at the bottom of the screen. I've written down single terms of a series. Of course, you could also use the sigma notation to abbreviate this. So what can we actually use the Taylor series for? Well, let us go back to the very beginning again and think of approximating functions using polynomials. In the graphs that I showed you, you saw that the Taylor polynomials approach the function f as the degree of the polynomial increases. The approximation got better and better the bigger n was. And in fact, it turns out that the Taylor series, T of x, for our function, is exactly the same as f of x, at least when x is close to 1. So we can think of the Taylor series for this function as a new definition of the logarithm. And this is mathematically quite important. So now we have two ways to define a logarithm. It's either the inverse of the exponential function, or we could say, okay, the logarithm of x is given by the Taylor series. We can also use the Taylor series to compute complicated limits. On the slide you see a rather complicated limit, namely the limit x goes to 1 of logarithm of x, this is our function, divided by the square root of x minus 1. So obviously the square root of x minus 1 is only defined when x is greater than 1, so we assume that x approaches 1 from above. X decreases towards 1. Now why is this limit complicated? Well, let's have a look at the functions making up this limit. Log of x at 1 is 0, but square root x minus 1 when x is 1 is also 0. So we have a limit of the form 0 divided by 0, which is a complicated case and we cannot say straight away what the limit will be. And this is where Taylor series come into play. How do we do this? We just use the Taylor series of log of x, which we had on the last slide. In fact, we only need to use the first terms. The Taylor series of log x starts with x minus 1 minus 1 half x minus 1 squared, and so on and so on. And now we sub this in instead of log x. And you see, now we can divide each of the terms of the Taylor series by the square root of x minus 1. And we end up with square root x minus 1 minus 1 half x minus 1 to the 3 over 2, and so on and so on. And these are terms that we can compute the limit x goes to 1 of. Because when x goes to 1, then square root x minus 1 goes to 0. And so do all the other terms. So we don't divide by 0 anymore. We now just have a sum of terms that each goes to 0. And this means the limit x goes to 1, log x over square root x minus 1 is 0. We can also do computations with Taylor series. We can add them, we can subtract them, we can multiply them. And we can also differentiate and integrate them. And this is a nice method to get new Taylor series. So let us have a look at how this works. Let us differentiate our Taylor series t of x with respect to x. So I want to differentiate x minus 1 minus 1 half x minus 1 squared plus 1 over 3 x minus 1 cubed, and so on and so on. I can differentiate each term in the series separately and then consider their sum again. If I differentiate x minus 1 with respect to x, then I get a 1. If I differentiate minus 1 half x minus 1 squared, I get 2 times over 2 x minus 1 squared. So this is just x minus 1. And I have the minus sign, so I get minus x minus 1. And so on and so on. The next term will give me x minus 1 squared plus sign. And then I get x minus 1 cubed with a minus sign again. Now this is a series that looks very familiar because it is a geometric series. And we can actually use the sum formula for the geometric series and find that this series gives the function 1 over 1 plus x minus 1. Now the 1's of course cancel, and we get the function 1 over x. This series only converges when the modulus of x minus 1 is less than 1, which means x is not too far away from 1. But of course this was our assumption for the Taylor series in the first place. So the derivative of t of x with respect to x leads to the function 1 over x. Now of course this is not very surprising because the derivative of the logarithm is 1 over x. And so you see there's an equivalence between differentiating the Taylor series and differentiating the functions. And in hindsight probably you could say in order to get the Taylor series of logarithm of x, it might have been easier to start with the Taylor series of 1 over x in the first place and integrate this one. This would be another possibility to compute the Taylor series of log of x. Taylor series can also be used to solve equations, algebraic equations or even differential equations, or at least get an approximation to the solution of these equations. But this will be dealt with in a different podcast. So let me just summarize at the end the method of obtaining a Taylor series for a function again. So Taylor polynomials and Taylor series are used to approximate functions near a certain point. This is sometimes called a local approximation. We have a general formula for the Taylor series, which you've seen on the slides. And all we have to do to compute the Taylor series or to compute Taylor polynomials, We choose a point A, or we are given a point A, depending on the problem, and we compute the function value and all derivatives of f at this point A. This might be difficult, not always easy, but in principle at least we can do this. Then we use these derivatives to form the sum n from 0 to infinity, the derivative of a of order n, divided by n factorial times x minus a to the n. We can either consider the whole series in a mathematical context. When we want to do something on the computer or with a calculator, then of course we cannot go all the way to infinity and have to stop at a finite degree and consider the Taylor polynomial. And you've seen that for degree 6 or 7, the Taylor polynomial already is a pretty good approximation to the function that we're interested in. Thank you very much.